Wonderful day, ladies and gentlemen. I'm very sorry for the technical difficulties that we have experienced. We're currently, as you can see, in our laboratory, and so we had to face a lot of technical difficulties to be able to give that to you live. To shorten down the introduction, we discussed yesterday our two main products, VALIMAT and IMPETUS, which the latter one we're going to discuss further today. With me are my two testing expert colleagues, Mr. Rimmermoser and Mr. Roland. And the second one of you will give you a short overview on our material characterization service. Mr. Roland?
I want to welcome all of you in our testing lab. The topic of today is the efficient dynamic testing with our hardware IMPETUS. As my colleague Mr. Schober mentioned before, as a short recap, we had yesterday some topics. Sorry, which switch is which screen? I'm just searching. So here is the right one. And I want to show you it first in a really short time because of the time is very short now. Some slides of yesterday, just our two products, VALIMAT software and IMPETUS our hardware. We have the possibility for the material characterization as a service. So here is the main goal to get validated material cards out of our dynamic testing possibilities in our lab. So at first we have our mold. So we produce in the main focus the plates and the specimen out of the mold and directly use it for our testing. Therefore, we have some standard packages for the material characterization service. I know this was also shown yesterday, and we also have this in our homepage at the slide down at the material characterization. You can also download some informations in detail. The direct link from the software and the material characterization is now set up to the hardware, where we have all the hardware setups as we mentioned before for the material characterization. So we have the basic, where we can investigate the strain rate dependent of material. Main focus, of course, are plastics. In addition, we have the standard package with some additional testing. Main focus is here for the failure and the damage to investigate this later on in the material card. The latest invention is then the professional package with additional information out of the dynamic tension test. So now we have the two tools to reach the main goal that we can produce validated material cards out of our testing. Some technical specifications. I don't want to go here in further detail. Some shorten up information is the upper right information, where we have the main information of the maximum energy we can achieve with our test system in the hardware. So we have the impact velocity in the range of 0.5 up to 4.4 meters per second, and can also mount additional mass to get to the high energy of 50 joule in the range of 1.5 up to 3 kilograms. The next step is that we have also the possibility to mount a high-speed camera, which is also integrated in our hardware and software. Here we have done different setups from the NOVA system, from the producer Photron. We are mainly using in our testing lab the NOVA S9. This is for the sensor is all the same, and the full resolution with the maximum frames per second are slightly different, and we can achieve in our systems with the setups about 20,000, 30,000 frames per second, but you will see it later on in detail on live testing. Additionally to the high-speed cam, you need, of course, for this an additional light device, which the information will be shown here down. So the first step of the testing is, of course, our software. So I want to show you just a short step of our software, how we start when we go to testing. So I just switch my position, and it's the moment I'm here at the 3-point bending test system. And here we have the software. And in detail, I want to show some detailed information about the upper left window. Here you can see different settings from the material with the different load cases, and you have also the possibility to set up the groups and also choose different number columns and which information you want to show. Here we have now the whole setup of such an template database with the different load cases from the 3-point bending for the temperature 23 degree and the different velocities. So here you have the possibility for different informations you can also show or hide. The groups you can also change in a right easy way, but our recommendation is just easy sort and less information will be enough. Don't need to show all columns. So therefore, I just want to filter number filter. So I choose just the 1 meter per second of the velocity. And here you can see we have prepared from the template database these tests. And I just want to show how you can also import the separate measured data information of such an test. So here you have test specimen name, the information of each specimen of the thickness, and as an average value, the width and the length of a 3-point bending specimen. For each specimen is also measured the mass, and it is mentioned for a support gauge length for 40 millimeters. So now I just copy, switch to the software, and say in the software I want to import in the database. I just switch in the full screen so you can see the whole drop down. So I'm here in the database and now go to import database value from clipboard. And here we can see that then the numbers are slightly different and the information can here seen. The moment these were 10, this 1, 2, 4, 5, 6, these were just 7. So you have to check just 7 with the header. Copy this one. And just repeat it to import, and then they are in the software. So as you see, it is very important that these informations from the test specimen are available. Of course, for the 3-point bending, the thickness is the main focus that for each specimen should be measured. Next step, which will my colleague show to you, will some additional informations of preparing directly on the hardware. And I will hand over now to my colleague.
Yeah, I also will welcome you here to our second day for a summer school with a little bit delay. And I shortly will talk about the measurement technique of our IMPETUS system. In this IMPETUS system, we are using different measurement types. The most important thing is the acceleration sensor on the pendulum head. So we are using an acceleration sensor. As you can see, the blue sensor on the pendulum head to measure the acceleration of the pendulum head and calculate out of them the force of the impact. We are using a second acceleration sensor on the counterbearing system to get the information of if there is a movement of the whole system or not. So if everything is fixed on the system, there should not be an acceleration on the counterbearing. The third sensor what we are using is the angle sensor in the upper area of the machine. Here we are using an angle sensor with a very accurate measurement technique, so we can measure the displacement of the pendulum arm of about 0.01 millimeter. In standard package of 3-point bending, we are using a 2 millimeter a pin with a 2 millimeter radius, and we are also using a support radius of 2 millimeter. The swing hammer mass is important because we are calculating the force out of the acceleration and the swing hammer mass. Therefore, we have a swing hammer mass of 1.5 kilogram. As my colleague Michael have mentioned before, we can add some additional mass to increase the mass, and this will increase the impact energy. Here you can see a short slide of the result, what we are getting from our measurement. We see the red line. This is always the acceleration of the pendulum head. We have the blue line, which is nearly zero. This is the result of the counterbearing system. And we have a green line. This is the angle sensor. But now we will switch over to the interesting thing. We do a live test of a 3-point bending. Yes, so we see our pendulum right here in the lab. And now we will perform a 3-point bending test. So in this image, you see that we have mounted the 3-point bending counterbearing in our pendulum, and we have a swing hammer without additional masses and mounted a 25G acceleration sensor on the pendulum head. The first step, what we have to do when we are, rise the camera a little bit. the first step before we can test is that we have to check this if there is the right sensor on our pendulum mounted. Therefore, I will show it in the software. In the software, you see the 3 sensors. We have the angle sensor when we are moving the arm, and we have 2 acceleration sensors, the 25G sensor mounted on the pendulum head and the 5G sensor mounted on the counter bearing. So we will check if this is the right sensor. We go to the sensor settings. Here we have a drop down where we can choose different sensors. Now we bring the pendulum arm up to 90 degrees. So we are raising the pendulum arm, checking it, that we are on 90 degrees. And in this position, our acceleration sensor have to be 1G. So we're doing a automatic calculating. Go to calculate automatic offset. The software calculate the offset of the sensor. Now we have to check this offset with to bring the arm into the vertical position. And the software is checking if this is the right sensor, because now we have 0G on the sensor because we are using a uniaxial acceleration sensor. That means we're just measuring in one direction of the sensor. The calculate was finished, and now we can perform a test. To perform a test, we will select the prepared 3-point bending test. So I will choose a 3-point bending test of a PP talcum forced test piece. I will perform a 3-point bending test with the mass of the fin, a radius of 2, no additional mass, and with a velocity of 2.5 meters per second. Here you see another important input. This is the distance of support gauge length. Now we will check the support of the pendulum. I will show it to you. So we are switching to this window. So it's important that we have the right support distance. Therefore, we are measuring our support distance right on the pendulum, and we have 40.02. This could be the input dataset 0, 2, 3, and we can save the test. And now we are able to perform the test. Therefore, we are using a sample with a dimension of a length of 50 millimeter and a width of 10 millimeter and a thickness of 2. We are inserting just this test piece in our counter bearing like this and bring the pendulum arm in contact. This angle is so-called the contact angle. So we get the contact angle, and up from this angle, we are calculating the correct height of our pendulum arm that we are impact at 2.5 meters per second. And on this angle, the pendulum stops automatically. Now we got the start button. Safety screen is closed, and we go to start. Now the green button is green, and we can perform the test. We'll show it to you on the live view. And now the test was performed. Here we got a successful test. And now we can have a look on our measurement curve. And zoom in, and we see our acceleration signal of the pendulum arm and our angle sensor. When we evaluate this test, we can load plots and now get directly a force displacement curve of this test. And we see also the strain curve. Okay. That's how we perform the 3-point bending test. Now I quickly will show you how we handle the tempered test. So for a test conducted at a high or low temperature, we are using this sample magazine. It's an aluminum magazine, and therefore we have to insert our test pieces like that. Just I will switch to the big window. You can see it. Okay. So to perform the test at the high temperature, we put in the samples in the correct order, our sample magazine, just like that. The whole setup. After that, we are closing the magazine. And now here you can see the samples in it. And now we give this in the oven, like that. Here it's about 4 hours in the oven that we have the right temperature. When we have to test at 80 degrees, for example, we temper the samples at 82 degrees. So to be higher than we will test. Now, meanwhile, we have to prepare the database correctly. So we have to prepare our tests in the correct order, something like that. We will select our test, and now we insert a so-called dummy. We are inserting a so-called dummy probe to get the contact angle. We got the pendulum arm in contact, close the window, and starting the measurement. So we go contact angle and go to the set angle. We are raising the pendulum arm up to 2.5 meters per second and go to start. When this message pops up, now we can open the safety screen and take out our dummy probe. That afterwards we can test it with the tempered probe. I will show. So we will take out the test piece of the oven and put it in our isolation box. In this insulation box, we lose not much heat. So we can easily move out the test piece and insert it in the counterpairing system. Close the window. Go to start and perform the test within a few seconds. So the test was performed. I hope this shows a little bit how we perform the tempered tests. Okay, as you can see here, now we will change the 3-point bending setup to a compression setup to perform a compression test on a foam, and you will see how fast it will go. For this, we just have to mount this bar in the counterbearing system, and we have to change the fin from the 3-point bending fin to the compression fin. I will show it like that. For this reason, we just have to open a few screws. These screws also have to be tightened up when you will change the support distance. So you have to tighten up the screws, and you easily can change the support distance in the 3-point bending test, as you can see here. So now we have changed from 40 millimeter support distance to 30 millimeter. But we will change now to the compression test. So we're removing the counterbearing radius like that. Second time, and we have to open the whole counterbearing. With 4 screws. In the pendulum, as you can see, we are using a T-nut plate to fix our setups. Now they are free to move, and we will just add our counterbearing like that, and we have to fix it. One and the second time. And change the position. Like that, and we fix it on the T-nut plate. Okay, that's all. And of course, we have to change the fin of the pendulum arm. To change the fin of the pendulum arm, we have to tighten up the acceleration sensor. And for the compression test, we also will change from the 25G sensor to a bigger one to a 50G sensor. So I have screwed down the 25G sensor and will just add the 50G sensor. These sensors are plug and play. That means while the software is running, I can change the sensor easily. Change the fin with 1 screw. And now I have dismounted the fin of the 3-point bending, and I will mount the fin of the compression test. So that's all. Now we will fix the new 50G acceleration sensor. With 2 screws. In the standard package, we're including a 25, 50, and 400G sensor to cover a big range of accelerations, because you have to be sure that your measured signal is in between 10 and 90% of the full scale of the acceleration sensor. Now we have changed everything, and what we have to do is to set up the sensor in the software again. Therefore, we are raising the arm up to 90% as we have done before. Like that. Go to the sensor settings and choose the right 50G sensor. That. And now we have to calculate the offset again. Bring the pendulum in the horizontal position. Software calculates the acceleration. Now we have to bring the pendulum arm in the vertical position to check the sensor. The software is checking if we have selected the right sensor. And the calculation was successful. Now we have changed the sensor, we can see here. And we quickly will perform a compression test. Therefore, we are using a PUR foam. We are using a 20 to 20 millimeter cube, and this cube sticked on the contact bearing. Like that. And we can perform the test as the same as we have done before. Okay, so now I've created a new dataset, and I will perform the test at 1.5 meter per second. To perform the test, it's the same procedure as on the 3-point bending test. We just have to bring the pendulum arm in contact with the test piece. We have to close the safety screen, and we can go to contact angle and I go to contact angle and set angle, and now the software shows to raise the pendulum arm up to this decision velocity of 1.5 meter per second. I pull up the arm, and the arm stops automatically in this high. And now we can go to start the test. The button is green. I will push the button, and the test was performed. Data saved. This was correctly, and here we see the measurement curve. Measurement curve. It's interesting that we see a big exclamation mark on the side, on the left side of this dataset. That means that we are in a high range with the measurement curve. So as you know, we have mounted a 50G sensor, and we are up to 50G. That means we are in the upper limit of the sensor. And I will evaluate this dataset. You will see the result. And we directly got the force displacement curve of this compression test. And we got in a big compression. And also we see the stress strain curve like that. That was the compression test. And now we will continue with a few minutes break and continue after that with the puncture test and the dynamic tensile test. So see you back in 5 minutes.
Yeah, I want to welcome you back from our short coffee break. Now we have the topic for the dynamic puncture test. I will shorten up a little bit because of the end time of 11 o'clock we want to reach. So here we are at our second device, which is really prepared for the puncture test. And I switch now really into the software of the puncture test. Here we have, as mentioned before, the dataset prepared, and at the moment I'm searching for the mouse cursor. And here we have different materials, and I have prepared in the clamping device of the puncture test material PP. Here we have the plates, just prepared out of our 120 millimeters per 80 millimeters, 2 millimeters thick out of our mold. And I switch in another view of software. Here we have the high-speed camera just connected, and the live view is running. I'm updating just the shading, and here you can see the live view of the resolution of 640 to 640 pixels. The camera is set up. So just want to show you another view of the cam inside. Here you see the counter bearing of the puncture test, where you can easily just put in the plates prepared. And this is also possible to preheat or pre-cool, same as Stefan showed before in the case of the 3-point bending. So same procedure as shown before. I just go into the contact angle and go in the data set. You can see back in the full screen, the right one. That is the contact angle on set angle of the desired test velocity of 4 meters per second. We rise up the pendulum arm until just break, and we can just start the measurement and have to mention that the lights are ready for setup, and the trigger will also show and start. So here you can see that the measurement is done. In the background, we also have downloaded the pictures from the high-speed camera and short show the application of default. And load the plots. As you see before, here you have the punctures of the specimen, the pull-through of the fin of the specimen, and here we have the rest energy consumption of the puffer system on our pendulum head. The second one I want to show is the test from the camera in the viewer of the measurements. Here we have the high-speed images. It's stored frame by frame. And herefore we have a separate Python script. Just showing and wondering you don't see it. So here we have the test we performed at the moment. The Python script we are using is the create high-speed video. It's just using in the background the data we are storing in defined arrays of the database and also the ASCII files on the system. And now we are correlating our measured data directly to the frames. So now it's executing, and we are finished with the whole procedure of the puncture test video. And we just update the view, go in detail that you can see a little bit more. Here we have the high-speed video, and just showing you again, here you see the video high-speed puncture test correlating with the test data. So this was just a short overview of directly implemented of the high-speed camera on our test system. And the next topic will hand over to my colleague of the dynamic tensile test, and he will give you a short overview. We'll hurry up in the slides a little bit.
So we have seen the puncture test of my colleague, and now I will really fast talk a few words of the new efficient dynamic tensile test. This tensile test consists mainly out of 3 parts. We're using a counter-bearing system where we have a force load cell included. So in the dynamic tensile test, we are measuring the force directly by a load cell and not with the acceleration sensor on the pendulum arm as we do it in all other test setups. We are using a really smart fixture of the test piece. We are connecting these jigs on the test piece just to really fast hang in the sample in our counter-bearing system. So we are able to perform high and low temperature tests also in our dynamic tensile test. Of course, we have the third part is the pendulum impact head, where you can see here. So it's easy to operate. As I mentioned, we are measuring the force directly, and what we have to do in the dynamic tensile test is that we have to measure the strain locally on the test piece. So we are using DIC for that. But I will switch over to the live test of this dynamic tensile test, because this is the most interesting thing, how fast we can perform the test. Here, see what we have to do before we perform the test. We have to bring on a speckle pattern on the test piece and fix it. Hang in the counter-bearing system and can do the test automatically. We calculate the DSC measuring. Okay, so I will switch over to the live test. Okay, so now we are here on the pendulum arm and the pendulum for the tensile test, as you can see here. What we have to do is to fix this prepared test piece with our in our checks, front and data. So we insert it like that. Put on test piece and prepare the test. Just a few screws. It will go really fast. And the front check is also fixed with 4 screws. And that's all what we have to do. So now we are ready to test this sample, as you can see here. To test, just have to hang in the sample in the counter-bearing system like that, and have the same procedure as we do it at every test. We bring the contact angle, the pendulum arm in contact with the test piece. We have to close the window here we have a black window because of the bright light what we are using for the DSC, as you can see here. I go to contact angle, rise the pendulum arm up, and perform a test at 3 meters per second. I go to start, activate the lights on a low level, and press the green button. Here was a light flash. The test was performed. We are downloading directly the images, as you can see. The images was downloaded. In the background, Mercury, the DSC software, is directly calculating automatically the DSC strain measurement field, as you can see here. This is done within a few seconds. It's a very ductile material. It's a EP. So we are performing and calculating the DSC directly. Here we have the failure of the test piece, and the calculation was finished. We're creating a video automatically of this calculation. And this was finished, and all data now will be copied to the dataset in VALIMAT. And so we store all data, all raw data, all images directly in VALIMAT in the dataset. And this is finished. Go to OK. And we now quickly evaluate the test. That's the measurement. So do you like that? We have to evaluate it. And we can plot the result of the tensile test, as you can see here, directly with a strain curve. Okay. So I think we are running out of time, so we are on point at 11 o'clock. And now I will quickly hand over to my colleague, Christoph, and I'm really thank you for your attention, and I hope we could give you a short impression of our testing system in our lab. Thank you.